you. So yes, so let's start with a brief recap of what we said yesterday. And so what we studied in rigid implicit space, and then L is the radius of our hyperbolic space. And one thing is that we can take the scales that are associated to our massive quantum field theory, let's say a coupling G, for instance, and by normalizing the couplings at the scale given by the radius of our space, we get new dimensionless parameters. Okay, so you can think of this as the RG flow stops at the IR cutoff of my space, and this gives me a parameter G hat. And the important is that in this space we have these asymptotic observables, which are the boundary conformal correlators, and they look very much like a CFT in one lower dimension. In particular, we have data like the scaling dimensions of the operators and the OP coefficients, which now will be functions. Okay, so we will have a continuous family actually of CFTs, which depends on these parameters G hat. Okay, and they will also depend. They will also depend on boundary conditions. Meaning that, in general, for a given value of G hat, there might be multiple ways to place my theory. Even though I fix the back theory, there might be multiple ways to put it in the background of AdS, and these multiple ways might give me different value of these observables. Okay, so this is the choice of boundary condition. And yeah, so this continuous time, as a function of this parameter, I can go all the way from perturbation theory when the parameter is small to the flat space limit, which is the strong coupling limit, because perhaps what we are most interested in. But it's nice to have this additional new node, let's say. And then we just briefly review the free scalar example, which perhaps many people already know from AdS CFT, but just in this fancier language of boundary data that depends on the parameter. Okay. So for the scalar, the boundary condition for this massive free scalar is on this form, or this parameter delta satisfies the equation. Okay, so this is the mass in units of the radius. And then this means that there are two solutions for this delta, which are associated to indeed two different boundary conditions. Okay, so for a given value, I have two possible boundary conditions. Now it turns out the one that has dimension smaller for most values of this parameter is actually below the unitarity bound. So this is why I employ it dash, because it exists in a sense. While there is only one, this plus boundary condition, that is actually the one that exists in the flat space limit. And then at some point, like in this small region between the Bertalanffy-Friedman bound and Bertalanffy-Friedman bound plus one, they both exist. So I have an ambiguity. There are two ways now to place the scalar in AdS. And the fact that this new possibility arises is kind of important because it explains why there is an instability here. So the instability here, I can interpret it as there is this additional choice, and then the two choices merge and annihilate. Okay. I just want to point out that usually this language of two CFTs merging and annihilating, for some of you might have already heard it, usually it's phrased in terms of RG flows between CFTs. Okay. Also in this case, you can phrase it in terms of RG flow, because actually it turns out that you can take the boundary condition minus, and you can have an RG flow to the boundary condition plus in general, some coupling, let's call it Y. Now this is a boundary coupling, okay? So I'm not talking about RG flows in the bulk, I'm talking about RG flows at the boundary. So if you take the minus, let's see, and you turn on the boundary of AdS, you can turn on a deformation, which is the square of this operator, okay? The square of this operator, as I mentioned, in the minus boundary condition is smaller than D, so this is relevant. Okay, and you can also see this flow equivalently from the point of view of the minus boundary condition. The minus boundary condition is that the operator post squared is irrelevant. Okay, so it's the leading irrelevant deformation on this flow. And so let's draw this parabola from a different point of view, in the sense that we can think of it as the beta function for this coupling Y. Okay, let's imagine the beta function for this coupling Y. What I'm claiming is that this beta function has this behavior, and there are two solutions. One solution is the attractive fixed point is the minus boundary condition. The repulsive one is the plus boundary condition, okay? And then there is this G. This is now a boundary of G. And on the other side, there is the instability. What do I mean by the other side? There is the instability. So this is the beta function when this parameter m squared is larger than the beta non bound. But then if I make it bigger, I increase, sorry, if I decrease m squared, at some point, what happens is that the plot becomes like this. Okay. So these 2 points, these 2 solutions that are 2 AdS invariant boundary conditions, 2 boundary conditions that are compatible with the isometries of my space, they get closer and closer, and then they stop existing, become imaginary. Okay. And at that point, they are only float this unstable point. Okay, so this is another point of view of the same thing, which from the point of view of boundary of G. Now, today, I finally want to get to gauge theories, which I wanted to be main application.
Sorry.
Yes?
What does happen when one of the 2 theories is non-unitary?
So if you sit here,
Yeah.
I mean, if you're okay with violating unitarity, nothing special. I mean, here that you can compute all the correlation functions, and it's still going to be a generalized free theory. So definitely there is no big deal in, I mean, we can study a generalized free theory with the non-unitary value of the dimension. It's just that, yeah, for my, I mean, I wanted to consider like the case of really a quantum theory where I want to impose unitarity, then this is not allowed. Okay. So you see there is a big difference though between this part in which everything is real in my spectrum, just that I violate unitarity bounds. It's different from what happens when you go past this point. When you go past this point, you have a couple of, if you want, of complex boundary conditions with complex conjugate data. Okay, so if you want, it's a even bigger violation of unitarity.
So if I want unitary, so if I am considering a unitary theory, I want basically a UV completion when in my RG flow when the theory is non-unitary.
You mean if there is a way to somehow add stuff to make this unitary?
Yeah.
Well, one thing that you can imagine, let me see if I sent you too much. So yeah, maybe what I want to say also. So here I'm not sure how to add stuff to make this, because I mean it depends what you mean by this. I mean, if you mean that the dimension is so small, in any case you're going to violate unitarity. There are cases in which, for instance, this instability, the stability in this part of the plot, this could be cured, for instance, by adding a quartic coupling, right? Because if you add a quartic coupling, what is going on here? So, in the scalar potential, if I just do free theory, I took it to be just this, right? And I'm telling you, when this m squared is too negative, you have instability. And if you add a quartic coupling, then actually we have a new boundary condition that arises, where the scalar has some non-zero value of the boundary, and this would cure this instability. So here, instead of flowing to something unstable, it would flow to this boundary condition. Okay. But yes, this one, I'm not sure that this one is just okay. Any other question? Yes.
Regarding the boundary operator expansion, so looking at that.
Yes, exactly. Yeah, this you should think about it as a boundary operator expansion. Yes.
In the case of the free scalar, it's simply just the dual operator that's being exchanged was the sense that if I now consider like a pi to the 4th theory.
Absolutely, yes. Then you're going to have more stuff.
You can have more stuff.
Yes.
If I now ask what is the CFT data, I know the prescription for any value of G, with an argument for expansion.
Exactly.
How do I do it? Is there a prescription to compute the boundary operator product expansion coefficients?
Well, I mean, in principle, you can do that. I mean, sorry, what operators appear in the BOE? perhaps from the point of view of computing the BOE is more direct to think about it in terms of what are the possible bulk boundary to what function, right? Then you can ask yourself, what operators can I place at the boundary such that this two-point function is not zero, okay? So in free theory, this is the only diagram that you will have. And so this is just the boundary model of the scalar. If you now have lambda phi 4, for instance, you can start drawing more diagrams. You can have some diagram like, let's see, below, something like this, okay, for instance. So this tells you the operator that maybe we call O cube, now is going to appear, okay? And you can do this like reliably in perturbation theory. If you ask me what is the BOE non-perturbative, it is, I mean, I don't know, it's a hard question.
But there is a prescription. Because that reminds me of like
Is it clear that the diagram is the growth? Just is it propagator, then the vortex interaction? Okay.
because that's computing in a Winton diagram, you compute correlation function. Here you're actually computing the value of phi at a given value of the coupling, the sum of each coupling.
Well, I mean, I just have a theory in which I'm computing with the spectrum of the theory at some point here.
Yes.
And I'm doing it using perturbation theory. And I'm going to be able to compute the BOE coefficient order by order in this expansion. So I'm telling you that this BOE coefficient starts at order lambda 0, this one starts at order lambda to the power 1, and if you want, you can compute it even higher order. But yes, one comment that maybe is useful to compare with the DSMT. In the DSMT, we always talk about dual operators. What this means is that in free theory, and in free theory, there is only one operator in the BOE. Okay? So as soon as you turn on interactions, it's not really one operator. Okay. Any other question? Otherwise, I will move to page theories. So let's now be ambitious and go directly from free scalar to needs.
So maybe a way of replacing that,
Yes.
you don't have the concept of the source. You just have the BOE at the bottom.
What do you mean the source?
Because the DSFT have one operator, but you also need to turn on the source for the operator not to exist with.
No, right. I mean, yes. So I think that's like a bit of a, in my personal opinion, the way it's phrased the calculation of things in the DSFT with this source is a bit of a historical thing. Like I much prefer this people call extrapolate dictionary, in which you just say that you take the operators and you push it to the boundary and you see what happens. Then yes, I mean, it's of course the European point of view. Like yeah, in the way you learn, I don't know, from the old literature, suppose you want to compute some frequent function, right? You would compute the partition function as a function of the source and then take the derivatives. I mean, of course, you can do without sources. You can just say that.
Not sure, but
You-
in
you
the
compute-
DSFT, the equalities between the partition function with the sources in the string side and in the CFT.
Well, or you can also place it without ever talking about the partition function. You can say that the scattering of gravitons in type 2P is correlation function in equal 4. I mean, I would need to use the word sources to say this.
No, but yeah, but for example, in that parabola would make sense in DSFT in the sense that the negative one, the red one is with the source, is not.
No, yes. I mean, also in Q15 AdS, I can, if I want, talk about the partition function in presence of the sources. When I turn on the sources, I will break the AdS isometries,
I see.
but I can do that, yeah, for sure.
Okay, thanks.
It will be like saying that, you see, there is a more general boundary condition. Here, the boundary condition is basically saying that I set to 0 this C number, right? You can consider a more generic boundary condition in which this C number J is not 0. And this would be a boundary condition that doesn't preserve the isometries because this is mass scale, but you consider it if you like.
I see.
Okay. So let's do now needs. So I want to consider 4 dimensions. To be concrete. So we know this function. Is up, yes. And so just to set up some notation. I have the algebra valued, but again, some generators. Generators of some the algebra G. So G, big G the group. And this is the algebra of this group. Okay. I'm choosing the normalization. What is this like? Is like this. And that really not is usual this time, okay? Which has this piece minus A coming later. And this not me. This is something strange. So far there is not much difference between the one you learn in tasking. Let's also introduce a notation for the gauge transformations. So the gauge transformations, so there is a gauge redundancy in this theory. Which says A mu in omega, A mu omega minus 1 plus I omega d mu omega minus 1. So now omega is a function that goes from our space to the group, right? Just a brief recap of the physics of this theory. So the physics of this theory is that it has energy. So far, let's then we are going to use L to span over this energy, but let's say in flat space. You can think about it as energy that goes from free gluons, right? We have a tier of free gluons in the UV. Then the coupling runs, and we end up with a gap IR. Okay, gap means that there is nothing at all in the deep IR, right? The theory, all the particles are massive. And so the big change happens at a scale, which is the dynamically generated scale. Okay. So this thing you can think about it as this one loop, as this part, right? So it's an energy invariant scale. You take the derivative of this with respect to mu, when it is 0 to a loop. I'm using the fact that the coupling runs. So this C is just the facilitated representation for SUL and so this N for SUL. Let's say NC for SULC. Okay, so what am I saying? Let's recap. So I'm saying this coupling is classically marginal, but then it has a negative beta function, so it's actually relevant, right? And then the theory flows to strong coupling. And what we know is that the actual physics, so naively you look at this Lagrange and you say, ah, this is a theory of free gluons, but then what actually happens is that you have a spectrum of massive glue balls. Okay, and these glue balls have some masses. Okay, I runs over the glue balls. There are some bound states, if you want, you can think about it as some bound state of the gluons. And where there are some order 1 numbers here that give you the mass as a function of the head. So you can ask ChatGPT to tell you what are the lattice results for these numbers. It will very easily print it out for you. So okay, so of course the holy grail is to find some way to compute these numbers, right?
Lorenzo, just a quick question about
Yes.
the gauge group. Since you're gonna put the gauge group on AdS, are you gonna discuss what boundary conditions?
Yeah, that's gonna be
gauge
like
group?
most of what I'm gonna discuss. Like depending on the boundary conditions on this, we're gonna have to decide what this function does at the boundary of AdS. Yes, that's important. Okay, and just to be sure, like these states, these massive proofs, the states, these massive states are these states are G singlet. Okay, so which is what we call confinement. So, okay, probably you know this from your PhD, but just I want to say that the dramatic story here is that you start with this theory that looks like you have massless particles of spin 1, which carry some indices under this G, and then the actual result is that you get this massive bound state with some hard to compute masses, and they are all singlets of G. Okay, which is what we call core confinement. So core confinement is a statement that all asymptotic states are singlet. Okay, there are various notions of confinement. So this color, I'm just using this to specify that I mean this notion, the notion that the asymptotic states are singlet. Okay, there are other notions of confinement which are related but logically independent. For instance, what is the potential between probe quarks? Okay, that's another story. But
You know, there is a story about the covariant states in QCD.
oh, really? I don't know what the.
Because, so it depends a little bit on the boundary conditions that we decide on the gauge group. And people in the 70s, they were making two choices. One is to make the gauge group to go to 0.
But in what setup? You mean some
No, in flat space.
okay.
So you define, you're still in flat space. You do temporal gauge so that you go like some Newtonian gauge. And then, depending on whether the gauge group goes to 0 or goes to some constant at infinity, you have two possibilities. Because if it goes to 0, then it's not cannot wash out the global colored states.
Yeah, okay.
And the global color is compatible with gauge invariance in this case.
Hey, you're anticipating what I'm gonna say now. Yes.
Because then if it goes to constant, then we can wash out.
Yes.
And then people were trying to find these things on the lattice.
Okay.
But on the lattice, you cannot find them.
Yeah, I mean, I think that if anything, like the fact of putting it in AdS allows you to be a little bit more sharp of what you mean by the boundary conditions and what happens at infinity. Because maybe in flat space you can start saying, okay, if the Euclidean, what do I mean? Infinity is 1 point.
The point at infinity. So
yeah, the point
at infinity.
Here instead, we can discuss a lot about the boundary. The boundary is very clearly there inside your face. So yeah, I mean, it would be very interesting if we discover that there are two sets of asymptotic states for real mills depending on some boundary condition. But at the moment, I think it's not what we believe. Okay, so now what do we do in AdS? So let's follow our strategy, the same as for the fixed scalar. So now we're going to have some very, let's keep writing them every time. So we have this dimensionless parameter, right? That we can use. And another question becomes, what happens as a function of this lambda hat? Okay. So here we have some regions that we would like to explore. It's a hard region. Here we have some weakly coupled gluons in AdS. And here perhaps we have we expect to have Brugger's right in AdS, but which means that from them approaching the flat space limit, that just have this bunch of massive particles in AdS. Okay. Now, I want to stress that this condition of confinement, it tells us something strong here because it basically just what are the asymptotic states now, thanks to the bar state boundary operator correspondence. Okay, it's basically like saying what symmetries recognize the spectrum of boundary operators. Okay, so here, one thing that we know, one thing that we expect is that for confinement means that there is no G symmetry acting on the boundary operators. That's the implication. Okay, of course, we cannot prove for confinement, that's what we expect. We expect that there is color confinement, which means that there is no G symmetry. Now, let's do what we are best at doing, which is let's analyze instead the weak part of the weakly coupled part. And then our goal will be to try to find a consistent picture all the way. Questions about this? This way.
So in the case when lambda is actually strong, you still say that the DOE, even in terms of the same degrees of freedom, you start to do it?
Well, I mean, I would say that it's going to be very hard to use the Lagrangian to do any
Yes.
computation here. But one thing that I kind of know is that I expect to have operators which have some dimension, okay, that grow linearly with L, right? So remember, this is just the limit of large L of the relation we saw for the scalar, right? This was the relation. Now imagine you take L large, right? So this means that with fixed M, for a fixed M, this means that delta is also large. So what I expect in this part, I expect to have operators that are very heavy and exponentials that go linearly with the radius. Okay, so that's one thing that I can say. And this thing should be color singlet.
Okay.
Then how to exactly obtain it from the OP, that's a different question. Now, let's for a second analyze this part and let's see what we can say. So, let's consider the possible boundary conditions for when this lambda hat parameter is much smaller than 1 and we can rely on perturbation theory. Okay, so again, when we can rely on perturbation theory, boundary conditions are found by requiring that the action is stationary on the equations of motion, right? So we take the variation of the action, we impose the equations of motion, they are mixed equations in this case, and then we find this boundary term. So there's an integral of the boundary of maybe you can let's put it at some z equal epsilon just to regularize a little bit. Then you have trace of f z I times delta ai. Okay, so I is now 1, 2, 3 is an index parallel to the boundary. Okay, I have a three-dimensional boundary. This and z instead is the radial direction. I just copy. This is z and this is x1. Okay, now we want to find some boundary condition that cancels this guy, right? And it needs to be compatible with the equations of motion. So if you look at the equations of motion, they're actually the leading term for z going to 0, it looks like this. Okay, so the equation of motion for 0, okay? Which means that the leading term in this the boundary behavior of the gauge field must be linear, right? So there are two possible modes for the gauge field, and you can also easily compute from this HeI, and you find that this JI. Okay, so just to be sure, I mean, these are just now the arbitrary function of x. These are just the leading modes that are allowed by the boundary by the notion of motion. Now, the boundary conditions means specifying what these two coefficients do, in such a way to set to zero this boundary term. Okay. So, okay, let's see. So one very natural possibility is what we call Dirichlet boundary condition. What is the Dirichlet boundary condition? It means that we fix this AI to 0. Okay, so we kill this model. Okay, and then instead the I is an operator that is free to fluctuate at the boundary. So in this case, the theory of our AI takes this form, and as a result, when we compute this variation at the boundary, we leave 0, and this sets the variation of the action from 0. You see, if that AI is 0, I kill the variation of the action, I'm happy. While the other term that appears in the variation of the action is FZI, the boundary is just is J. Okay, that's one possibility. Then the other possibility is another natural possibility instead is to do the opposite, right? Is to set FZI to 0 and leaving with what is called non-boundary condition. The other possibility is to fix the value of 0, then boundary behavior is like this, which means that okay, this means again that the action doesn't, the variation of the action at the boundary is 0. Okay. Now let's go a little bit more over these two simple boundary conditions and see what happens, what are the consequences. Okay. So let's study a bit more what happens with Dirichlet. So if I have a Dirichlet boundary condition, it means that I have this JIA operator boundary, and you can. Sorry, one comment. Maybe some of you are wondering what did I do with AZ? Okay. So I only consider the components of the gauge field parallel to the boundary. This guy basically fixed by my choice of the condition. And I will so that's why it's enough to tell you what this does, and this will not contain any information. Okay, so that's why I'm focusing on the parallel component.
But AZ does not have a DZ equation. Right?
Sorry, repeat.
AZ does not have an equation of the boundary.
Right. I mean, it's once you fix this and you have your gauge condition, you can determine completely, right? Because yes, I mean, yeah, that's it. Now, this operator you can see from this equation, right? From the boundary behavior of A, you can convince yourself that this J has dimension 2. Okay, scaling dimension 2, just from applying the usual isometry that gives you dilatations here. If I give this dimension 2, and it is a spin 1, right? Because it has one index, one vector index at the boundary. And this means that it is a conserved current. So if you're not familiar with this part, in general in CFTD, if you have spin 1 and dimension d-1, you must be conserved. Must be conserved. Okay? If you want to be infinity bounds. Okay, so we get a conserved current which is in the adjoint of our group G. So what did we get? We get a G global symmetry. Okay, so this is a very convoluted way, perhaps, of telling you what you learned the first lecture of AdS, that if you have gauge fields in the dark, you have a global symmetry. What always people forget to say is if you fix the Dirichlet boundary condition. Okay? So this means that you have G global symmetry. Boundary. Now, let me make contact with what Andrea was saying. What is this global symmetry? What does it have to do with the G gauge redundancy that we have in the bulk? Well, it has to do the following. It's just that because my boundary condition, okay, is not invariant. So I'm telling you now one way to understand this global symmetry. So it's not invariant under gauge transformations. Because remember, this guy will transform into omega, but it also has a non-homogeneous piece. It's something like that, right? So if you see, it will not leave this condition invariant unless omega is constant at the boundary. Okay. So if I take this omega to be constant, then this boundary condition is okay. And so this constant value of when 0 goes to 0, this approaches some constant, which now I can think of it as a parameter of a G global symmetry at the boundary. Okay, so I'm allowed to do this type of transformations. And okay, just one comment that if you want to maybe I don't go into these details because otherwise I will not have time to do anything else, but like if you want to make your current be normalized in the usual normalization that gives you word identities, okay, a small comment is that you need to rescale. So you need to rescale and write some okay, so this is the one. So you need to put this weird factor of 1 over G squared. If you put this factor 1 over G squared, this normalization that satisfies all the entities. Okay. What about the some questions about this?
What about the field?
The field strength.
Now transforms the same way as A.
So well, basically this boundary condition you can also rephrase it if you wish as a boundary condition of this guy. So this guy will approach this current J to boundary. If you take the parallel component, they go to 0. They go to 0 with a certain power.
Yes, but I'm asking
Uh-huh.
from the point of view of now it's the same object as A. It runs the same way. It should tell you the exact same information. Should anything.
The field strength.
Yes, because now since omega was fixed to be a constant.
Oh yeah. I mean, the way you should think about it is now this is the main object at your boundary. Okay. If you are actually coupling, you will have this and product of this with itself. So you can just rephrase everything in terms of this current. Okay. And also the field strength is going to be either this or derivatives of this, depending on the components you consider. Okay. Now, maybe one last thing that I want to say about this before going to normal is that in this word identity normalization, when you compute the the two-point function of this curve. There is this parameter Cj, okay, which is the global symmetry central charge. There's some tensor, so some of the indices, and everything else is fixed by the conformal symmetry. So this is now power 4. So this is a famous object we consider in CFT when we have concurrence, because since we can use ordered identities to normalize them, this coefficient is meaningful. Okay. So I just want to tell you in this particular example, this Cj comes out to be a number divided by G and H's. Okay. So why am I telling you this? I just want to tell you that the weak coupling expansion for the Dirichlet boundary condition, if you want, you can also, if you're more familiar with this CFT language, you can also think about it as the large Cj limit. So large Cj is that the perturbative limit. Okay. Now, let me go to the Neumann. In the Neumann instead, well, it's much less in a sense, what we can say. So, naively, we would say that this AI is an operator. Wait, AI is this, right? The bond of the. Naively, we would say it's an operator of dimension 1 and spin 1. Okay, we just use the isometries. But this would violate unitarity. So to make sense of it, you actually need to declare what is the right point of view. The right point of view is that actually now I can keep omega at the boundary to be x dependent. Okay. Why can I keep it to be x dependent? Because now my boundary condition is this. Okay. But this object transforms homogeneously under H transformations. So this boundary condition is left invariant if I do a H transformation at the boundary. Okay. So in other words, so this is compatible with G, which symmetry at the boundary. So in other words, now I should think of G is gauged also in the boundary. And that fixes this problem because now this object here, which seems to violate unitarity, is actually not gauge invariant. Okay? It's actually not gauge invariant. So if you want to now do compute some, obtain some gauge invariant operator, you have to, for instance, start doing the fixed strength. I mean, the fixed strength itself is still not gauge invariant, right? Because the fixed strength is not gauge invariant from Abelian theory. So you need to do rather sophisticated things, like this would be your simplest example of a gauge invariant operator at the boundary. Okay, into traces of f. So f, I'm just calling lowercase f is the fixed strength of the lowercase a. Okay, the boundary fixed strength. Okay, so let me summarize what are the boundary conditions. Dynamic coupling. Sorry, some what we said now.
Can I think of that as a background field in the boundary?
Well, you can think, I mean, it's more like it would be a background if you're in Dirichlet, it would be a number that you can turn on. Well, in Neumann it's fluctuating thing, right? It's your degree of freedom at products. And so boundary. We currently have this option, which is D, Dirichlet and Neumann. And in this case, the boundary correlators at decoupling are basically a generalized free theory of the operator HeI. Okay, it's a generalized free theory of a current and with global symmetry. Global symmetry G. Then I have this non-boundary condition, to which the boundary correlators of decoupling are a bit of a weirder beast, which is not often studied, which is a generalized free theory of this strange gauge field modeled by the G gauge symmetry. Okay. And so in this case, there is no G global symmetry. Okay. Questions?
Are these operated related by Schneider's transformation?
Last question. Okay, so this is dimension 1, and this is this is dimension 1, this is dimension 2. So yes, 2 is 3 minus 1. There is no, as far as I know, one analog of the thing that we made in scalar theory flowing from one to the other. It's more sophisticated how to interpolate between these two boundary conditions. It's going to be part of the issue. Okay, so now we can.
You cannot still interpret similar with Francesco's question. Can we still interpret A as like a source? Just
Yeah, in this boundary condition, this, I mean, this is always the case when you have these free setups. In the free setup, what is a dynamical operator in one of the two, then typically is the source of the other one. Okay. Now, I'm going to finish it, but just let me phrase what is the problem that then one would like to solve. Okay. Can I erase everything? Like somebody is fine. Okay. Erase here. Let me try to trace the problem. Question. So now we have we can draw again our plot as a function of this lambda. Okay, and now we can populate also the free part. So in the free part, we have this Dirichlet boundary condition. We have the Neumann boundary condition. Okay, and then there is some mysterious blob here. And then a strong coupling. We have this, let me call it confined. Okay, with the boundary condition with glucose. Okay. And we would like to understand how to connect, okay? How to go from one to the other, because this in principle could be also useful to then, I don't know, for instance, if I want to set up some extrapolation to compute the mass of the glucose, okay? So understanding the physical confinement in AdS means understanding what happens here in the middle. And so it's immediately obvious that this D cannot be connected with the confinement, with the confined boundary condition, right? Why it cannot be connected? Because this boundary condition is a set of continuous TFTs which have G global symmetry. So, in other words, the D boundary condition is deconfined, right? All the asymptotic states are colored, so it can not happen that this line continuously connects here, that's for sure. For the normal one, we can be more optimistic, okay? We can hope that indeed this sort of the continuation of decoupling of the confined boundary condition, okay? So let me now tell you what are various proposals for what happens in between, and then today or tomorrow I will tell you how we tested these possibilities, okay? So let's begin this. Maybe just as a further bit of motivation, in my opinion, like understanding what happens to this D and how come instead this other thing comes out, it's really a sharp way to think about like confinement emerging, right? Because this Dirichlet boundary condition is really the naive expectation from the Lagrangian. I have blue ones that I can scatter, I have color asymptotic states. So understanding how this thing dies off and stops existing in flat space, to me, it's conceptually one way to say, okay, now I understand how confinement arises. Okay, I understand it as an increased radius.
But can we observe global color? Meaning that, you know, if the universe like in some colored
Okay, you are more open-minded than I am. Like I was really taking the box like from the knowledge of what I was taught in 50 courses, that the thing is like this. I have G singlet states. So you want to say that actually you're a bit more open-minded to the possibility that there could be colored asymptotic states for your means.
because there is no, you know, not only issue the edge invariant, and I'm not sure you can observe global color.
What do you mean you cannot? I mean,
It's like some of the reflection set, like, you know, some universe, which have like different color charges.
but the question is, it's really whether we can have colored asymptotic states. So it's a definite well-defined no statement, whether you have it or not. And I was always taught that you don't have. So if I believe this, then it means that this Dirichlet boundary condition must lie in some way. No?
You know, Young Mills, well, I don't know. I never understood this story because Young Mills, you see, you can only simulate it on the lattice. And on the lattice, because of the boundary conditions, you wash out all these colored sectors. But people discussed on the lattice this issue, for instance.
You're saying that it could be that it's just that we are biased from the fact that on the lattice we don't
It's biased by two things. That in nature, we cannot observe blue balls because the string breaks because of dynamical quartz. So we don't know anything.
Yes.
And Young Mills, when you put it on the lattice, people study it, and then on the lattice, they are washed out by the periodic boundary conditions and the fact that nothing is periodic and so on. And you know, pure Young Mills by itself, I don't know. I mean, I want to understand.
So let me turn it around. I can tell you that we perhaps were biased by this and we already expected to have only
Well,
colored
that's one
singlets.
option. Yeah.
But indeed, we do find, okay, not strong, I cannot prove it at the moment, but we do find some encouraging hint that this boundary condition did disappears. Okay, so this would be, if you want a way to, to actually say, you can actually see that you do not have colored asymptotic states. Okay. We don't have a proof, okay, so I'm not questioning. But we see some hints that it happens. Okay, so what are the possibilities for this connection? Okay, so one possibility is similarly to the Bretton-Friedman bound from the scalar, if you want. So we can have some merger, and annihilation. Okay, so this is the one that at the moment I find most likely. So I start with the one that I like the most, and then I'll tell you other stuff. Okay, maybe I should put lighting into the story. Okay. And so this is the idea that perhaps there is another boundary condition which we didn't see at decoupling, perhaps because it's non-unitary. Okay, but then at some point it pops into existence, and then it meets with Dirichlet, and the two of them die at some critical value. Okay. While the Neumann boundary condition happily continues its life and it becomes the global boundary condition. So the name we gave to this mysterious thing is D star. Maybe I should mention that first of all, this clash between the Dirichlet and the confined should give credit. It was observed in paper long time ago by Aroni, Cruz, Tong, and it's very difficult. Young Kirillevich. Okay, so they are the ones that said that there is kind of mystery of how to connect. Okay, so one possibility is that this happens like this. and some critical value. So you should think about it as after this, Dirichlet becomes unstable, and there is some bubble of the confined vacuum that comes and takes over, and then you go to the normal boundary condition. So just sorry, maybe we'll take some 5 minutes.
Yeah, sure.
We can draw a similar picture of this merger annihilation from the point of view of boundary RG. Okay. So from the point of view of boundary RG, this means that this star should have RG flows in both directions. So there should be some boundary coupling, and we call it Y, like we did before. And this operator O should be relevant in this star, irrelevant in D, okay, in such a way that they have. And so we expect this when lambda is smaller than the critical value, it should have these fixed points, which are the repulsive one, the attractive one is Dirichlet, and then somewhere here there is fine. Okay, for the sixth relation. So this star is kind of a phase transition between normal and Dirichlet. Okay. And then as you increase it at some point, as you increase, you go below the critical value. What you find is that it says there is only one real possibility, which is the confined boundary condition. Okay. So that's possibility one. Seems pretty economical. Now, what is a signature of this? The signature of this is that this operator O is a singlet, okay, of the global symmetry, because otherwise I cannot have this, otherwise will break it, the G symmetry, and it must become marginal precisely at this point, okay? Actually, maybe I forgot to say it before. Like before in the free scalar, we have the operator O squared, right? That will become marginal precisely the operator Friedman bound. Here you see this operator must be relevant on one side, irrelevant on the other side. So when the 2 points meet, how do I see it? I see it because O becomes marginal. Okay. So this is signaled O by singlet O becoming marginal. Which means it has dimension 3. Now, another thing that can happen though is principally it could be that there is some colored operator.
But maybe just a question about.
Yes, yes.
In the GFF, purely GFF case, we could see the non-unitary case by studying the equations of motion. Here, do we see that this star?
Well, I mean, I can tell you some ideas that we have, but we don't have at the moment. At the moment, there's nothing in the literature that is completely proposal for this. We have some ideas, but we are still checking if they make sense. So we think that indeed this could be something non-unitary that then. I mean, this would mean that there is more boundary conditions that will coupling, which will be beyond the 2 that you already told you. But this we kind of know. I mean, I never claimed that DNN are the only possibilities in existence.
Yeah.
Because, for instance, you also have boundary conditions in which you take N and you couple it to some degree of freedom that are local. Those are infinitely many possibilities that exist. And among one of them, perhaps you can find this to start. Okay. Now, another thing that can happen, which would complicate the picture a little bit of this connection, is that you can have some kind of what we could call higgsing transition. Right? Let me explain what I mean there. Suppose some operator O with some index here, which means it is charged under G. Okay, so this A is some index of some representation of the color group becomes marginal at some point. or becomes relevant. So process marginality and becomes relevant beyond some point. Then what could happen is that your from your Dirichlet boundary condition, a new branch of boundary condition pops out. It's a bit more complicated, which you can call this its boundary conditions, which are obtained flowing with discharge operator. So you add the boundary, this operator, and you break the symmetry, right? You're breaking the symmetry G because you bring one operator that is charged. Okay, so it's breaking the G symmetry. Now, notice that Dirichlet keeps existing after this point. So the Dirichlet boundary condition is still the fine-tuned point in which this y is 0. Okay, so I'm not in this scenario. I'm not telling you really what happens to Dirichlet. I still need to explain what happens to Dirichlet. But what I mean by this is that it's possible that the setup is much more complicated. Because, for instance, if I have now this H boundary condition that doesn't have G symmetry because I broke it, in principle, this could also connect to the confined one, because the confined one has singlets. But how do I know if maybe it's just because everything got Higgs and I just have massive states? Okay, so it could also connect to the confined one. In fact, if you look at the definitions of confinement, people sometimes tell you that this notion of color confinement cannot tell apart higgsing and confinement. Okay. Yes.
So this new state would be massive or massless?
This boundary condition.
Yeah, because breaking the symmetry, I expect a Goldstone boson, right?
No, because this is, yeah, very good. So I should have mentioned two things. So Dirichlet, another reason why it can never be connected to this is that it has a state which is the current, which is protected dimension delta. So this state would always lead to something massless in flat space because the dimension doesn't increase. Okay. Now, what's happening here is not a symmetry theory, it's a higgsing. So what happens is that this curve is now in the H boundary condition gets an anomalous dimension. So the dimension starts increasing. So it is totally possible that this H is completely massive. Okay, so that's why it can connect to the confined boundary condition. Unlike D always has a gluon, always has a massless gluon, and the massless gluon cannot connect to the confined boundary condition. Okay. Finally, let me mention the last possibility that people considered. Okay, people propose new ones, but another one would. It's a bit more esoteric, but in principle, it could also be that our CJ is the coupling, sorry, the normalization of the Dirichlet function of my state, right? Remember, I have this proportional to CJ. So this coefficient here, it could be that it goes to 0 at some critical value. Okay, so what does this mean? It means that actually this you should think about it as gluon normalization in AdS. So this could be like saying that the norm of the gluon one particle state goes to 0 at some point. And when I have null states, usually what we say is that we quotient out the stuff that's becoming null, and I just restrict to a subsector. Okay, so I need to quotient out whatever that means. The gluon, and actually you can easily convince yourself that all the colored states need to be quotiented out in this case, and all the color states, and remain with a singlet sector. So people call this scenario was proposed in the original paper by Aron et al. G singlet sector. People call it decoupling. In a sense that the blue one becomes null and decouples from the rest. Okay. Okay, so maybe I can stop here just to tell you what we're going to see tomorrow. So tomorrow we're going to see that using numerical bootstrap, we can rigorously rule out this possibility. Okay, so this thing cannot happen. You cannot continue to go to 0. So in a sense, it's less interesting. And then using both perturbation theory and numerical bootstrap, but this time is not as conclusive. But we can see that the possibility 1 seems a little bit more likely. And this complicated scenario which start Higgs seems not be happening. Okay. Okay. So who's today? Oh, sorry.
No, we didn't. Let's try to the
When I think of decoupling, I also think of orthogonality between the one stage and the rest of the global space.
Yes.
That seems wrong, and that requiring that one state is itself null.
Yeah, the ground state is itself null, and you can also check that you can figure now a charged state. So you say you injection some charged operator, and you consider this 4-point function. These exchanges. Okay. So in the progressive normalization, you can check that this, the contribution of the block of the current going to go like 1 over J. Okay. So when this knot goes to 0, this also means that all of the correlation functions of the polar states blow up. So you need to get rid of all of them.
But can one say a weaker statement, like the matrix elements of any one state with the rest of the theory is 0 without imposing that the 2-point function is null? So just orthogonality.
I think that could be another possibility, perhaps. Actually, I did something that at some point somebody has told me this idea. I mean, it could be that what happens is that actually the Dirichlet boundary condition just decouples into parts. One is the blue Bolson, and one is on the decoupled color sector. Yes, on that is something we haven't really found constraints on this scenario. So this maybe, I mean, I would find it a little bit conceptually less pleasant because it would still, in a sense, have colored asymptotic states.
It's just the default.
Yeah, just the
In a sense, is kind of what we're saying. It's like a selection sector.
Yeah.
Colors scenario.
Yeah. You study adjoint QCD in the 1+1 dimension, doing, you know, 1D bootstrap.
Yes, you can. I think it should be done, yes. But we haven't done it yet, yes.
Was there Clever is doing a lot of
No, absolutely. If don't use it in English.
1+1. The gauge field is 1+1.
Sorry?
The gauge field is 1+1. A different set, but because you have a logarithm.
Yeah, no, certainly there are differences. Like the Dirichlet boundary condition, it's basically there is this with the Dirichlet is from dimension 4 above, and Neumann is from dimension 4 below. And so if you go to 3 dimensions, and I think it too is a bit, maybe you can do some fine tuning, but if, for instance, in 3 dimensions, you cannot have the Dirichlet boundary condition. It breaks IGS isometries. So the questions you can ask are a little bit different, but you can still study it. Yes. I mean, for instance, you can ask, if you reproduce some of these results about the masses or
Does it buy you something to do some large dimensional expansion and some concepts?
This we didn't consider. Maybe I'm not so familiar with large dimension, but yeah, probably there is some simplification. Maybe you mean large dimension of space time?
Yes.
Yeah, we didn't think about it, but maybe it's. Yes. Yeah, I mean, of course, if you study higher dimensional gauge theory, then the problem is the opposite, right? It becomes strongly coupled when AdS is small.
I see, right. Yeah,
So it would be like, no, but maybe it's fun to also study the setup in which if you have an effective field theory, everything is under control when AdS is large. Then you try to ask what happens when you make it smaller. It does not accept so much.
So just to summarize conceptually, what's happening is that in the confining phase, you have the boundary safety as kind of separation. Everybody is super.
Yes, exactly. So you somehow you find a way that your boundary safety connects to this strange boundary condition in which, from the point of view of a safety tree, is very strange. You just have these singlets which are extremely heavy and nothing else. Yes. Yep.
Okay, let's thank again, Lorenzo. So as yesterday, there is the lunch break upstairs. I will ask you to bring your stuff with you so that I have to go back and forth. Asking you what you're talking about.
Smash on the door.